Download this code from codegive.com, link in the description below. OK, let's dive into the fascinating world of integrals. This will be a comprehensive guide, covering various types of integrals, their properties, and providing Python code examples using the sympy library. Table of Contents *. 1. What is integration? A quick review. 2. Basic integration concepts. 3 types of integrals. 3.1. Definite integrals. 3.2. Indefinite integrals. 3.3. Improper integrals. 3.3.1. Infinite limits of integration. 3.3.2. Discontinuous integrands. 3.4. Line integrals, path integrals. 3.4.1. Line integrals of scalar fields. 3.4.2. Line integrals of vector fields. 3.5. Surface integrals. 3.5.1. Surface integrals of scalar fields. 3.5.2. Surface integrals of vector fields, flux integrals. 3.6. Volume integrals. 3.7. Multiple integrals, double and triple integrals. 3.8. Contour integrals, complex integration. 3.9. Lebesgue integral. 4 Integration techniques. 4.1. Substitution, use substitution. 4.2. Integration by parts. 4.3. Trigonometric integrals. 4.4. Partial fraction decomposition. 4.5. Numerical integration, quadrature. 5 Using sympy for symbolic integration. 6 Code examples with sympy. 7 Conclusion. 1. What is integration? A quick review. Integration is a fundamental concept in calculus that essentially reverses the process of differentiation. It's a way to find the area under a curve, accumulate quantities, and solve various problems in physics, engineering, statistics, and many other fields. The basic idea is to divide a region into infinitely small pieces and sum them up. 2. Basic integration concepts. Integrand the function you're integrating, the function under the integral sign. Variable of integration the variable with respect to which you are integrating, example x in indefinite integral f, x, dx. Limits of integration the values that define the interval over which you are integrating, only for definite integrals. Constant of integration a constant, c, that appears in indefinite integrals because the derivative of a constant is always 0. 3. Types of integrals. Here's a detailed exploration of different types of integrals. 3.1. Definite integrals. Definition A definite integral has specific limits of integration, a lower limit a and an upper limit b. It represents the area under the curve of the integrand f, x, between x equals a and x equals b. Indefinite integral sub a slash sub b slash sub f, x, dx equals f, b, f, a. Where f, x, is the antiderivative of f, x. The result is a numerical value. 3.2. Indefinite integrals. Definition an indefinite integral does not have specific limits of integration. It represents the family of all antiderivatives of the integrand. Indefinite integral f x dx equals f x plus c, where f x is an antiderivative of f x, and c is the constant of integration. The result is a function. 3.3 Improper integrals. Definition An improper integral is an integral where either one or both of the limits of integration are infinite. The integrand has a discontinuity within the interval of integration. Improper integrals require special treatment involving limits. 3.3.1 Infinite limits of integration. Indefinite integral sub a slash sub infinity slash sub f x dx equals lim sub t rightward arrow infinity slash sub indefinite integral sub a slash sub t slash sub f x dx. Indefinite integral sub dash infinity slash sub b slash sub f x dx equals lim sub t rightward arrow dash infinity slash sub indefinite integral sub t slash sub b slash sub f x dx. Indefinite integral sub dash infinity slash sub infinity slash sub f x dx equals indefinite integral sub dash infinity slash sub c slash sub f x dx plus indefinite integral sub c slash sub infinity slash sub f x dx, where c is any real number. 3.3.2 Discontinuous integrands. If f x has a discontinuity at x equals c, where a c b indefinite integral sub a slash sub b slash sub f x dx equals lim sub t rightward arrow c sub dash slash sub indefinite integral sub a slash sub t slash sub f x dx plus lim sub t rightward arrow c sub plus slash sub indefinite integral sub t slash sub b slash sub f x dx. The integral converges if both limits exist and are finite. Otherwise, it diverges. 3.4 Line integrals, path integrals. Definition A line integral integrates a function along a curve, path, in space. The path is often parameterized by a parameter, usually t. Line integrals are used to find the work done by a force along a path, the mass of a wire with varying density, etc. 3.4.1 Line integrals of scalar fields. Let C be a smooth curve parameterized by r, t, equals, xt, y, t, z, t, where a less than or equal to t less than or equal to b. Let f, x, y, z, be a scalar field defined on C. Then the line integral of f along C is indefinite integral sub c slash sub f, x, y, z, ds equals indefinite integral sub a slash sub b slash sub f, x t, y, t, z, t, r, t, dt. Where r, t, equals square root, dx slash dt, sub 2 slash sub plus, dy slash dt, sub 2 slash sub plus, dz slash dt, sub 2 slash sub, is the magnitude of the tangent vector to the curve. ds represents the arc length element. 3.4.2 Line integrals of vector fields. Let C be a smooth curve parameterized by r, t, equals, xt, y, t, z, t, where a less than or equal to t less than or equal to b. Let f, x, y, z, equals, p, x, y, z, q, x, y, z, r, x, y, z, be a vector field defined on C. Asterisk then the line integral of f along C is indefinite integral sub C slash sub f dr equals indefinite integral sub A slash sub B slash sub f r t dt equals indefinite integral sub A slash sub B slash sub p x t y t z t dx slash dt plus q x t y t z t dy slash dt plus r x t y t z t dz slash dt dt. This represents the circulation or work done by the vector field along the curve. 3.5. Surface integrals. Asterisk definition asterisk a surface integral integrates a function over a surface in space. They are used to find the mass of a thin shell, the flow rate of a fluid through a surface, etc. 3.5.1. Surface integrals of scalar fields. Asterisk let S be a smooth surface parameterized by r, u, v, equals, x u, v, y, u, v, z, u, v, where, u, v, lies in a region D in the UV plane. Asterisk let f, x, y, z, be a scalar field defined on S. Asterisk then the surface integral of f over S is sub S slash sub f, x, y, z, ds equals sub d slash sub f, x u, v, y, u, v, z, u, v, r sub u slash sub times r sub v slash sub do dv. Where r sub u slash sub equals r slash u and r sub v slash sub equals r slash v are the partial derivatives of r with respect to u and v, and r sub u slash sub times r sub v slash sub is the magnitude of their cross product. This gives the area element ds. 3.5.2. Surface integrals of vector fields, flux integrals. Asterisk let S be a smooth, oriented surface parameterized by r, u, v, equals, x u, v, y, u, v, z, u, v, where, u, v, lies in a region D in the UV plane. The orientation is determined by the normal vector. Asterisk let f, x, y, z, equals, p, x, y, z, q, x, y, z, r, x, y, z, be a vector field defined on S. Asterisk then the surface integral of f over S, the flux of f across S, is sub S slash sub f ds equals sub d slash sub f, r, u, v, r sub u slash sub times r sub v slash sub, do dv. The flux represents the amount of the vector field passing through the surface. 3.6. Volume integrals. Asterisk definition asterisk a volume integral integrates a function over a three-dimensional region. They are used to find the mass of a solid object with varying density, the moment of inertia, etc. Sub v slash sub f, x, y, z, dv. Where v is the volume of integration, and dv is the volume element. In Cartesian coordinates, dv equals dx dy dz. You would typically evaluate this as a triple integral. 3.7. Multiple integrals, double and triple integrals. Asterisk definition asterisk multiple integrals are integrals with multiple variables. They are evaluated by iteratively integrating with respect to each variable. Asterisk double integral asterisk indefinite integral sub r slash sub f, x, y, d, where r is a region in the xy plane and d is the area element, which can be dx dy or dy dx. Asterisk triple integral asterisk indefinite integral sub v slash sub f, x, y, z, dv, where V is a region in 3D space and dV is the volume element, which can be dx dy dz, dz dx dy, etc. The order of integration matters and should be chosen carefully based on the region of integration to simplify the problem. 3.8. Contour integrals, complex integration. Definition A contour integral is an integral where the function being integrated is a complex function of a complex variable, and the path of integration is a curve in the complex plane called a contour. Contour integral sub c slash sub f, z, dz. Where f, z, is a complex function, z is a complex variable, and c is a contour in the complex plane. Contour integrals are used extensively in complex analysis to evaluate real integrals, solve differential equations, and in various branches of physics and engineering. 3.9. Lebesgue integral. Definition The Lebesgue integral is a generalization of the Riemann integral, which is what we've been mostly discussing so far. It allows us to integrate a wider class of functions, particularly those that are highly discontinuous. Instead of partitioning the domain of the function, the x-axis, the Lebesgue integral partitions the range of the function, the y-axis. The Lebesgue integral is based on the concept of measure, which generalizes the idea of length, area, and volume. It's a more advanced topic typically covered in real analysis courses. It's particularly useful when dealing with functions that are discontinuous on a set of positive measure. 4. Integration techniques. Here are some common techniques used to evaluate integrals. 4.1. Substitution, use substitution. Principle This technique simplifies integrals by replacing a part of the integrand with a new variable u, making the integral easier to evaluate. 1. Choose a suitable u equals g, x. 2. Find do equals g, x, dx. 3. Rewrite the integral in terms of u and do. 4. Evaluate the integral with respect to u. 5. Substitute back g, x, for u to express the result in terms of x. 4.2. Integration by parts. Principle This technique is used to integrate the product of two functions. Indefinite integral u dv equals uv, indefinite integral v do. 1. Choose which part of the integrand to call u and which to call dv. A helpful mnemonic is linear, logarithmic, inverse trigonometric, algebraic, trigonometric, exponential, to help you decide which function to choose as u. Functions higher on the list are generally easier to differentiate. 2. Find do, the derivative of u, and v, the integral of dv. 3. Apply the formula and evaluate the new integral indefinite integral v do. 4.3. Trigonometric integrals. Principle These integrals involve trigonometric functions. Common strategies include using trigonometric identities to simplify the integrand and applying substitution or integration by parts. Use identities like sin sub 2 slash sub x plus cos sub 2 slash sub x equals 1, tan sub 2 slash sub x plus 1 equals sec sub 2 slash sub x, etc. Use reduction formulas for powers of trigonometric functions. 4.4. Partial fraction decomposition. Principle This technique is used to integrate rational functions, polynomial divided by polynomial. It involves breaking down the rational function into simpler fractions that are easier to integrate. 1. Factor the denominator of the rational function. 2. Express the rational function as a sum of simpler fractions with unknown constants in the numerators. 3. Solve for the unknown constants. 4. Integrate each of the simpler fractions. 4.5. Numerical integration, quadrature. Asterisk principle asterisk when an integral cannot be evaluated analytically, i.e., finding an exact formula, numerical methods can be used to approximate the value of the integral. Asterisk trapezoidal rule asterisk approximates the integral by dividing the area under the curve into trapezoids. Asterisk Simpson's rule asterisk approximates the integral using parabolic segments. Asterisk Gaussian quadrature asterisk uses strategically chosen points and weights to achieve higher accuracy. 5. Using sympy for symbolic integration. Sympy is a powerful Python library for symbolic mathematics. It can perform symbolic integration, differentiation, algebra, and much more. Here's how to use it for integration. Asterisk install sympy asterisk pip install sympy. Asterisk import sympy asterisk import sympy. 6. Code examples with sympy. Explanation of code examples asterisk. Asterisk symbol, x, asterisk creates a symbolic variable x. Sympy works with symbolic expressions, not just numerical values. Asterisk integrate, f, x, asterisk calculates the indefinite integral of the function f with respect to x. Asterisk integrate, f, x, a, b, asterisk calculates the definite integral of f with respect to x from a to b. Asterisk oo asterisk represents infinity in sympy. Asterisk subs, x, x underscore t, y, y underscore t, asterisk substitutes expressions for variables. In the line integral example, this substitutes xt, and y, t, into the function f, x, y. 7. Conclusion. This tutorial has provided a comprehensive overview of different types of integrals and integration techniques. Remember that integration is a vast subject, and mastering it requires practice and a good understanding of calculus fundamentals. Sympy is a valuable tool for exploring integration and verifying your results. Keep practicing, and you'll become more comfortable with this powerful mathematical concept. Good luck.